MySQL, Postgres, or even NoSQL database. So these are some common things that you get out of the box when you go to a public cloud. These are things you don't have to worry about. And if you have any worries about whether the cloud can handle your data, this is a graph showing the number of objects in Amazon's cloud storage by the year. And the last count, 2013, they had 2 trillion objects. Right? It is kind of almost doubling every year. The cloud's compute flexibility is, I talked about renting of hardware. And why is that very interesting, especially for big data analytics, is that analytics workloads tend to be bursty in nature. Right? The end goal of analytics is some kind of action that you take. And generally, that action you can take only certain number of times a day or a week. There's no point getting results every second because you just can't react as a business. So these workloads tend to be bursty. They occur either at weekends, Monday morning, or during working hours. So there are natural kind of patterns there. The other interesting point where cloud is very useful is most organizations struggle to predict what their usage is going to be 2-3 months later. How many of you have had struggle getting hardware for your projects, in terms of getting machines and so on? Okay, I see a few hands go up just a little bit in case their colleagues are around. But so that goes to show what happens is companies either overestimate or underestimate the success of the project, and so they size the size of the systems. And if the project is successful and more work comes in, suddenly everybody's got to get in a queue. The flip side of that is if the project is not going at the rate that you expect, a lot of stuff is sitting idle, right? A lot of companies tend to be a little defensive, so they tend to over-provision compute. So this is a little graph showing the actual usage of a big data cluster at a customer site. And what you can see is that there are hours in the day where it goes up, there are other hours where it comes down. And if you're an organization that's, let's say you're building an in-house system, you would provision for the peak, right? That line, that little green line that you see over there. Rest of the time, when the actual usage is considerably lower, you're paying for stuff that you're not using. Most organizations, it's well known that they struggle to hit even 30% utilization of their hardware. And how the cloud helps here is the cloud allows you to scale up and down. It allows you to say, from morning 9 o'clock to 5 o'clock, let me bring my system up, let me create a cluster of certain size. In the evenings, I'll make it smaller, and in the night, I'll shut it down, or whatever that cycle that works. The other part of the landscape changing, so that was a little bit about the clouds. The second part is about big data software. Right? There are many open source projects out there which are very useful to get the kind of outputs that was shown in the previous talk. The most popular one that everybody seems to know about is Hadoop. Hadoop was based off Google's MapReduce paper. It's pioneered at Yahoo primarily. Hive is a tool that sits on top of Hadoop. It provides a SQL interface on top of Hadoop. Presto is since most of you don't seem to know, it's out of Facebook, and it's a fast SQL implementation. I'll talk a little bit about both Hive and Presto, with maybe just a slide on Hadoop, just for completeness. All of these softwares are production ready. These are not like somebody's homework projects. They're production ready. They're running at scale at Yahoo, at Facebook, a number of these companies. Right. So a slide about Hadoop itself. As I mentioned, Hadoop is the open source implementation of Google's MapReduce paper. Google used its internal implementation to index trillions of web pages. They kind of open sourced the design, and Yahoo then took that and kind of built out Hadoop out of it. What Hadoop allows a programmer to do is you can write a program that and you write a program in a certain way, break it up into what are called maps and reduced phase, and then the system takes care of parallelizing it, takes care of running that on your laptop or on a 1,000-node cluster, right? So you as a programmer don't have to worry about a whole lot of problems that come up with computing at that scale. The framework kind of takes care of that for you. So this gives Hadoop the ability to run on and execute workloads on large amounts of data, and Hadoop was designed to run on cheap commodity hardware, and cheap commodity hardware at scale always fails, and so Hadoop was designed to be resilient to these kind of failures. A disk fails once in a while, or memory goes corrupt. Hadoop is designed to kind of recover from this and continue processing. And Hadoop scales. Right? There are known deployments of 30,000 nodes and above. Hive is kind of a sequel on Hadoop implementation, and a little bit of history on this. Facebook had a multi-petabyte warehouse. Right? They were storing all the information about what are the comments you're writing, what parts of the website you're clicking, what are the things you like, and so on. And they had 80+ engineers who were writing Hadoop jobs to get reports out of all of this data. This data was of the order of 25 petabytes. Right? So they had folks who could write these MapReduce programs, and it would run against this gigantic data warehouse. Right? But what they found was, even with 80+ developers, they had a lot of business people who wanted reports, and they all had to queue up because it's really rich data. Everybody wants to get to it, right? And so what they quickly found out is that files are an insufficient level of abstraction, right? Hadoop works at the level of, I have these files to process, but most business users don't want to even look at a shell, right? So Hadoop was too low level, right? And what a lot of people were used to was SQL notions like tables, schemas, indices, partitions. These are considerably well known, right? So what they did was Facebook started a project to implement SQL on top of Hadoop. The goal was give an interface that is familiar to analysts. At the same time, it has the power to run against petabytes of data, right? Your MySQL databases generally run on a few gigabytes of data, right? But you have the same kind of interface, you can run the same kind of SQL, but now suddenly you can run it against many petabytes. So now this becomes really, really powerful. You can open up all of this data to a large number of people in your organization. Right? So it allowed non-programmers to process data. Facebook then open sourced this project, and again, this Hive is known to be production ready. It processes more than 25 petabytes at Facebook, and at Qbol, where I work, Hive processes about 20 petabytes of data every month. So what does Hive do? Hive does a couple of interesting things. Hive allows you to describe data. And I'll get to why that is important, but let's start with an example. Let's say I have data in a bunch of files. What Hive allows me to do is it allows me to say, hey, my data lives in cloud storage in a specific location, that this data is in a delimited form. It is comma separated, or it could be JSON format, or it could be a number of other formats. Please create a virtual table on top of these flat files. Right? Once you do that, now once you have the notion of virtual tables, you can run SQL queries against it. So this is a little example. So what you can see is the three parts that I talked about. The bottommost line indicates the location. Where is my data? Right? I could have one file, I could have 1,000 files, I could have 1,000,000 files. Right? It doesn't matter. This description kind of encompasses all that. It says that this data is a text file. It is a delimited format, and these are the kind of columns that these files encode. Right? Apart from delimited format, Hive can handle a large number of formats: JSON, text, binary. There's other fancy formats like Avro, Protobuf, Thrift, and so on. Why is this important? This is important because analytics is often a downstream process. What do I mean by that? Let's say you're running a website, your Times of India, right, or your CNN. Your main job is to run the website. That's what gives you the business. Analytics is something that happens post facto, right? So the guys who, the application in this case, which is the website, writes logs, writes data in certain form. And you cannot, as an analytics part of the organization, you cannot dictate the format that the files come in. You just take it as is, right? Therefore, the analytics system has to be extremely accommodating of different data formats, of data missing data, generally data being dirty, right? So that is something which is kind of a very standard requirement of these sorts of systems. And the other part is conversion of data can be extremely expensive, especially if you're talking about many terabytes of data. It makes sense to process it in the form that it already is in. Right? So this allowing for description of data is a very powerful concept in Hive. The other interesting aspect in Hive is extremely extensible from a processing point of view. The first one was the description point of view. The second is a processing point of view. You can connect to external data sources. Your data doesn't have to live in files. It could live in a NoSQL database like MongoDB. Some of your data could live in a relational database. Some of your data, remember we talked about low density and high density data. So some of your data could live in other places. And Hive allows you to connect. Right. You can also write code to understand new fancy formats, though this is not something which is very common. You can write custom business logic in a variety of different languages, right? Why is this important? Because analytics, if it is to give you a competitive edge, chances are you want to do something which is not generally available. Maybe it's a custom algorithm, maybe it's custom tuning, and so on. And it could be written in R. It could be written in Python. It could be written, in languages other than SQL, because it's a lot easier to express certain things in other languages. Hive is extremely accommodating of that, and what you can do is you can do some of the processing in SQL, then move the data into R, do some processing, and continue, so on. So in that sense, it is extremely extensible. So this is a very simple example. What this allows you to do is it tells Hive, hey, read data from this table, then run it through this Python program, right? This program could in turn call out into models, score models, and so on. And finally, how does Hive execute queries? Why is it that it's able to process data of this scale? As I mentioned, Hive gives you SQL-like ability on top of this large amount of flat file data. So you can run a SQL-like query like select count star from a table. This query is parallelized using Hadoop as the execution engine. Remember, Hadoop is very good at taking a program and running it across a bunch of machines. So here's a little example. Let's say you're running the same count star on, let's say you have 10 files, right? You can send 5 of those files to one machine, which does a count of the number of lines in those files, and you take another 5 files and compute the count of lines in a different machine. These two operations can happen in parallel, and then you send these results to a single machine and just add up these numbers, right? Now this process is extremely scalable. What does this mean? If I throw more data, let's say instead of 10 files, it's 1 million files. I can also throw more hardware at the problem and get results in the same time, right? So as the data grows, it allows me to tune the amount of hardware that I'm throwing at the problem. And since this is commodity hardware, the cost grows in proportion. Right? So how does internally what Hive does is it takes a query, it splits a Hive SQL query into multiple MapReduce jobs. Right? It runs the first job, it saves the intermediate data into a distributed file system, then it runs the second job, and so on. So it kind of goes one job after another. each job is data parallel. What that means is each job partitions its input and processes part of it. Just like I explained the count star, right? So one machine could do part of the processing. I'll give you another little example, right? So the 10 files get broken up, and each of these sets are processed by 2 different processes. Each one, let's say, takes up 100 megabytes of memory. So this is in general the data parallel processing that gives you scalability. Now, this is very nice, but there is another kind of parallelism that exists apart from data parallelism, and that is task parallelism. How many are familiar with data parallelism and task parallelism? Okay, so then let me explain what task parallelism is using an example. Let's say I have 10 files I need to process. Each file can be processed independently, right? And the processing has to happen in 3 stages, right? So I take a file, I do some processing, let's call it T1, and to do that processing I need 100 megabytes of space. I do that processing, then I do T2, then I do T3. Each one of these, let's say, takes up 100 megabytes of memory. Now there are 2 ways we can execute this entire workflow. The first execution model is as follows. I take the 10 files, I run T1, it processes all of these files, produces the output, which I write into an intermediate storage. Now I run T2 against all of the intermediate data, and then I run T3, right? So this is kind of a very serial kind of execution. Now, what are some of the characteristics of executing things this way? At any point in time, only one of these processes, T1, T2, T3 are active. Therefore, I need 100 megabytes of memory. Right? I can stop and resume computation at any point in time. So let's say T2 completed. Now I just want to freeze this. I can come, since the storage is stable, I can always come back 1 month later and continue processing. Right? I don't lose anything. So you can stop and resume. It allows multiplexing of multiple pipelines. What this means is, let's say you've got your pipeline and I've got my pipeline, and there are 10 other people with pipelines. This system can process one of your jobs, one of my jobs, one of somebody else's jobs. So everybody makes progress. Right? That is multiplexing. It kind of keeps everybody happy. It can tolerate failures. Let's say T3 failed. Right? I can always rerun T3 because I had the input of T3 saved somewhere. So it has a lot of nice properties if you execute this way. However, there are a couple of downsides to it. The first one is every job is spilling its output, right? And that can be very expensive because you could potentially be writing hundreds of gigabytes to many terabytes of data, right? This can be expensive. And the time to first result is really, really high. Remember, I have to process all of T1 has to finish, and all of T2 and all of T3, and only then I get my first result, right? So these are 2 distinct disadvantages of this way of executing. The second execution model works differently for the exact same problem, right? I've got 10 files. Now what I do is I take a single file, right? T1 processes it, produces the intermediate output, and just passes it along through a pipe to T2. T2 in turn does the processing and passes it to T3. It's a single file, remember, right? And while T2 is processing the first chunk, T1 can start processing the next one. So this is basically a pipelined execution, right? This is also called task parallelism. This is a very well-known concept. You can see this in assembly lines. If you've ever seen an assembly line, this is the standard way that anything gets assembled, right? Whether it's a car and so on. You have a bunch of people. A single car comes in. Somebody puts a door. Then somebody puts a window and so on. Right? Now this way of executing has certain advantages and disadvantages as well. Right? It requires 3 times the amount of memory, right? Because all 3 tasks are active at the same time. Just like in an assembly line, you have to pay 3 people, right? Because all 3 of them are working at the same time. All of these tasks are taking up memory. However, there is no spilling, right? there is nobody who's writing intermediate data to disk. Therefore, it is a whole lot faster. Right? The first result comes out of the system as soon as the first file passes through all the jobs. So you get very quick early results. Right? However, you can't stop and resume because things are in flux. Right? You can't say, okay, you know what, I'm going to stop this because there's a lot of state that's built up. All of these workers are somewhere in their processing. So there's no good time to stop. And multiplexing is more difficult. And importantly, this cannot tolerate failures. Right? There's no checkpointing that is happening at different points in time. And this is where Presto comes into play. Right? Hive was the first execution model that I talked about. Right? Hive was designed to work in exactly the first way. Right? It has all the advantages of that approach, but it also has the disadvantage that it is a lot slower because of that reason. Right? And therefore, Facebook started this internal project to implement SQL on Hadoop using the second model. And that's kind of how Presto came about. And the use case here was, you have a lot of data, but not every query has to touch all of the data. So there are some queries or there are some statements which require you to join and process enormous amount of data. On the other hand, there might be some where I'm just looking at a few rows, or I'm just doing I'm looking at rows that or data that came in yesterday, as opposed to the last month, right? So that's the use case that was targeted by Presto. Presto was open sourced late last year, and it promised much faster query performance, right? It does a lot of interesting things. It does in-memory processing, aggressive pipelining. I already talked about pipelining. It has similar kind of flexibility in terms of data format. So the same data that Hive can work on, Presto can work on as well. However, you can't plug in user code at this point. Right? So a quick contrast between Hive and Presto, because both of them are SQL and Hadoop solutions. It's useful to kind of see where they differ. I already talked about the different execution models. Hive spills intermediate data to file system. Presto keeps all of it in memory. Hive can tolerate failures. Presto cannot. Hive does automatic join ordering. Does anybody know what join ordering is? Okay, so join ordering in a nutshell is if you write a query, a join of two tables, the order in which you write the join matters if your database or your system does not automatically reorder it. I'll just leave it at that, maybe since I don't have a whole lot of time. There's also a lot of SQL syntax that Hive supports that Presto doesn't today, but that's a matter of maturity. I think some of these will get fixed over time. And there are a couple of other points along plugging in custom code and data types, all of which are indicative more of maturity than anything else. However, the main point to remember is that Presto promised much better performance, right? And so we did some performance experiments, and we found that Presto was up to 7 times faster than Hive, right? This kind of this is indicative of the difference in execution models that we talked about. That's what gives it a whole lot of performance advantage. The downside, again, is exactly what we talked about as well. There are some queries that will just run out of memory because you're so memory intensive. Remember, the 3 assembly workers, everybody has to be up. You're using a whole lot more memory. Therefore, there's a chance that you would run out of memory. Yes. So yeah. Coming to that, I'll come to that point in a separate slide. So if I have to contrast Hive and Presto at this point in time, it's basically the difference between a garbage truck and a Corolla, right? And there's no disrespect anywhere. Both of these are very important vehicles, right? But both of them serve different purpose. Hive, you can throw a whole lot of stuff at it, right, and it'll still work, but it kind of moves slowly. If you want to go to a grocery store, you will take your car, you will not take a garbage truck. On the other hand, if you have a lot of data that you need to do very irregular kind of data and stuff like that, and processing, then you would probably use Hive at this point. So given all of this stuff, so if you had to start off on a big data project, a setup that we recommend that we've recommended to many people, and it's kind of worked really well, is use cloud storage as the ultimate source of truth, right? Wherever your data is, pull it into the cloud, store it there, dump it, forget it, and then kind of take your workload and split it into two parts. You have your heavy-duty queries, which will go to Hadoop, right? You start a separate cluster in the cloud, run Hadoop on it, and run your queries against it. And your more interactive queries, run it on a separate cluster with Presto. Now, one of the interesting things here is the cloud gives you the flexibility to do something like this, right? It's not only these two systems. There are a whole bunch of other open source projects that are out there, and you can try all of these projects out in parallel without affecting your production workload. It can run against the same data. That allows you to continuously innovate and try out new things. Now, one thing that the gentleman already pointed out is this is a point-in-time comparison, right? Things are changing. Hive is actively evolving. It's working on task parallelism with 0.3 with the Stinger initiative and so on. And that's something that you can read up. But Hive is also actively moving in the direction. Presto is also making rapid progress to remove some of the limitations that it has right now. Right? There are other open source projects in the mix as well that you can use. They're somewhere between these two. There's Impala, Shark, Drill, and so on. And all of this, as a consumer, you have a lot of choice, right? The good thing is the cloud allows you to experiment. You're not limited by the number of machines you have. You can always spin up new clusters, try out new things. So, to conclude my talk, big data analytics is becoming more accessible and affordable to everybody. Public clouds give you a whole lot of flexibility, and they change the economic model. It allows you to try a whole lot of different things. Hive and Presto are examples of systems that provide intuitive and powerful ways that you can interact with your data. And if any of this stuff interests you, you can just look at kubol.com, which kind of gives you a lot of this out of the box. And you get Hive, Presto, Hadoop as a service, so you can just click in and get access to all of this stuff. And we are also hiring in case anybody's interested. All right. Cool. That's it. Any questions? Sure, yeah. If anybody
files, does how one queries across, say, a database like an Oracle database, a relational database within the enterprise, and these files on the cloud? Do they provide a seamless way, a transparent way?
Yes, so they kind of do myself, but I know it's possible. So what both of these systems allow you to do is you can plug in external data sources. I already mentioned that. And you can then join data which lives, of course you have to be able to access it from wherever you're processing. With firewalls and all that kind of stuff. But assuming all those problems are solved, you can actually, and in fact some people do this, is to join data that lives in your database, relational database, and this is very common when you want to join transaction data with this low density data that I talked about.
Okay, and the optimization techniques that it uses are probably far better than what one could achieve if one were to actually try and do this at the application layer.
Oh, absolutely. Okay. Because at the application layer, because you're dealing with a lot of data, you have to worry about things like parallelism, and you have to kind of rebuild a whole bunch of things that are already there somewhere else in an open source project. So if you had to run something on hundreds of nodes, you kind of have to reinvent all of the wheel there.
Yeah, no, what I meant was, you run at the application layer, you take on the onus of actually running part of the query on, say, the data that resides in the cloud, then taking those results and then doing a join with.
Right, but yeah, that data could be substantial and your application will have to kind of handle that then.
That's true. So right. Essentially use Hive and Presto on the cloud, get the results and then join it with enterprise data. if we just left it to Hive and Presto to do that joint too with enterprise
Yes,
data,
it
the
does.
optimization there would still be far better, would be definitely better
Yes.
than what one would
Exactly,
achieve
yeah,
otherwise.
yeah, you're right.
Okay. Good, thank you.
On Hive being better or Presto being better, one better than the other, is real-time analysis of data, like analyzing a Twitter stream. I'll give you an example. So if you wanted to understand sentiment analysis on real-time Twitter feed, is one better than the other to use?
So going to the first point, when it comes to performance, the format of the data does matter, right? So if your data is in JSON form or text form, you spend a lot of cycles finding out where one field ends. There's a lot of parsing cost that is involved, and that affects overall performance, right? Which is why if you query MySQL for, it'll be a whole lot faster than if you query the same amount of data through Hive. There's a whole lot more work that happens if the data is in text form or JSON form. So definitely the data format matters.
So, yeah, assuming it's in JSON?
Yeah, it matters. So there are many cases where JSON is kind of like from an application point of view, the one who's dumping the data, JSON is the most flexible. But from an analytics point of view, it's kind of the worst format in terms of performance, because you have to read stuff, you have to understand what this unstructured data means. All of that is processing cost. So what some people do is they transform part of the data. Let's say they identify that most of my work goes in the hot data and transform it and so on. So that is a trick that some people use. Yes, you can do that with both.
Deficiencies with which it's currently faced with. Presto is trying to address its deficiencies. So if one actually had to make an investment, is it better to just wait for Hive because Hive started earlier, or is it better to just start using a combination of the two if one actually had to invest?
Yeah, so that's why I left it at the crystal. The good thing about let's say being cloud-based is it allows you to experiment and figure things out on your own. We have a lot of users who are trying out both, right? So they're running Hive queries. They're generally happy, but over time, when enough work accumulates and they realize, okay, some things are a lot slower than they want it to be, and they carve out some of that work and they're trying out Presto now, and it works a whole lot faster. It doesn't work for everything. It works for a subset, and it works much better for that subset. Now, it remains to be seen, though, like I said, both of them are kind of converging. I think we'll have to wait and watch. Yeah.
So hi, myself Santosh. So you were talking about Presto implementation in memory. So you get the entire data set in memory and then
No. So what happens is it can. The actual amount of data that you're reading could be of the order of petabytes. But let's say, if you're familiar with SQL, you could just use a where clause that eliminates most of the data. It's the intermediate data that is in memory. So the data that it's reading could reside on disk.
So how it compares with Apache Drill? I know Apache Drill is still in incubation, but
yeah, exactly. So it's Drill is much further behind, I think, from my point of view, than Presto.
But one biggest advantage of Drill, what I saw was it connects seamlessly with other relational databases and uses the engines of other databases like Oracle or MySQL or SQL, and then pulls out the data and then joins.
Yeah, so most of these systems also attempt to do that. They attempt to push some of the work. Let's say you're backed by a relational DB, they try to push in some filters, some of the work down.
Okay. So some of the execution is done on the relational databases?
Yes,
and then
so if the data source can do some of the work, then they try to push it down.
So Presto supports that?
Yes, Presto does support some of that stuff.
Thanks.